Okay, we got a couple of. We have two topics to kind of clean up from chapter 12, and then we will talk about the big topics, which are stereo and regio selectivity. Okay, anti-Markovnikov edition of HBr. This mechanism is going to be completely brand new. It's something that we will have to do for the next exam simply because free radical halogenation that we will talk about after break also will involve this type of free radical mechanism. So what we know is if you add HBr, what am I adding? H and Br. How? Markovnikov. But if I want to add H and Br anti-Markovnikov, what I need to do is either add hydrogen peroxide or I can add an organic peroxide where the hydrogens have been replaced by alkyl groups. Okay, and that's going to change the stereo selectivity, or it's going to change what we will call the regio selectivity of the reaction, making it anti-Markovnikov, and that means it goes by a completely different mechanism. Okay, so if I take the same alkene that we've been using at the beginning here, and I add HBr in the presence of hydrogen peroxide, what I will do is I will then add the H to the carbon with the least amount of hydrogens and the Br to the most amount of hydrogens, so anti-Markovnikov. So first thing we should do is explain how does that happen. And that happens because the mechanism is what's called a free radical mechanism. Now, we haven't done radicals yet because radicals come next semester, but I've moved that chapter up into this semester so it's more consistent with the other sections because their book has it earlier on. What is a radical? A radical is when a carbon has an unpaired electron. Okay. So instead of losing both pair of electrons like it does in an SN2 or SN1 reaction, it only loses one electron. And so this is a carbon radical. Like most radicals in life, they are not stable. And although they may be geniuses, etc., if we talk about non-chemistry, typically not stable. So why is this carbon not stable? Because it only has 7 valence electrons. It wants 8. Now, it is better off than a carbocation because a carbocation only had 6. So radicals then are stabilized the same way the carbocations were. If you want to stabilize a radical, what you need to do is to add an alkyl group to it. And if you do that, remember in an alkyl group radical, or in an alkyl group, period, the hydrogens are delta plus, the carbon is delta minus. That carbon having some extra electron density can now push it into the carbon that's now with 7 valence electrons. And that will push its electron density closer to 8. So, unlike primary carbocations where there's just too much ground to gain 6 electrons, 3 alkyl groups isn't enough to push enough electron density into a primary radical or into a primary carbocation. primary radicals are actually stable at room temperature. So in terms of stability, tertiary radicals are still more stable than secondaries, but primaries can form. So we are allowed to write the structure of primary radicals. Because again, they're starting at 7, which is closer to 8. With a carbocation at 6, it's just not enough. And all of the other radicals, for instance, we talked about if you had a carbocation next to a double bond, that even though this was a primary carbocation, it would be stable because it has resonance structures. By me taking both of the electrons here and moving it over, I can write that resonance structure. So this was called an allylic carbocation. The allylic carbocation is stable even if it's primary because it has more than one resonance structure. Resonance structures can also be written for allylic radicals. So if you have a CH2 here with an unpaired electron, you can write a resonance structure for this, and it's going to, and the way we use arrows in free radical reactions is a little bit different. And this goes all the way back. Remember, the book foreshadows a lot of things. So if you go back on Piazza about 2 months, you'll see that I actually wrote these resonance structures out because somebody had asked a question, hey, why does it say it needs 3 arrows versus just 1 for a carbocation? So they were trying to foreshadow that, and I doubt anybody remembers that right now, so they failed in trying to foreshadow this far in advance. So I'll do it again. And what happens is that instead of a full arrow represents the movement of 2 electrons. A fishhook half arrow represents the movement of 1 electron. So in this case, what I would do is I would split this double bond up, give 1 electron over here and 1 electron to that carbon. And notice I'm using the half arrow now. And then this unpaired electron on the CH2, I would use a half arrow to show that it's going to be paired up with the 1 electron from the double bond. And so in that case, what I end up doing is I end up moving the radical now to the left carbon and forming a double bond between the middle and the right carbons. So we're going to use the fishhook arrows today to write this mechanism because I'm going to move 1 electron at a time. Okay, and so that's a characteristic of a free radical reaction. We're going to have radicals and we're going to have half arrows moving electrons 1 at a time. Okay. So allylic radicals are more stable than just a single primary radical because of additional resonance structures. Okay. Everybody kind of with me? So that's what we have to know about radicals. Now, how we form radicals is by splitting bonds homolytically. So instead of breaking a bond and giving both electrons to one atom, I'm going to split the bond and I'm going to give each atom its electron back. So there are a series of steps that we go through. The first step in this case is what's going to be called an initiation step. And the initiation step is going to be that the hydrogen peroxide is going to split in half with this bond giving 1 electron to the oxygen and the other electron to the oxygen on the right. So because the 2 oxygens don't have an electronegativity difference, there's no reason for 1 oxygen to get both electrons and the other one to get the shaft. right? They're of equal power, so they're each going to get one electron. And so when we do that, we're going to end up forming then two hydroxy radicals. And the book may not use the hydrogen peroxide. It may use an organic peroxide. The same thing would happen. We would split the two, we'd split the oxygen-oxygen bond, and that would give us then two alkoxy radicals. And I'll talk about the relevance of this, like in biochemistry, at the end of this, but this happens all the time. Okay. So if I have a hydroxy radical then, what happens is it reacts with HBr. And so what it's going to do is, what radicals do is they abstract. Okay. They abstract hydrogens. That's what radicals do, and that's why they're really important in biochemistry, because we don't want that to happen. We don't want free radicals, and if you've heard free radicals, in popular nutrition literature or in biology or in genetics, free radicals roaming around our system abstracting hydrogens is not a good thing, right? Because we don't want our DNA have hydrogens abstracted from them and all of a sudden we end up with a mutation, because most of those are not good, right? Unless they give me some sort of superpower like dishes or laundry, it's not going to be helpful. Okay? It's going to lead to a mutation that's probably bad. So we have to have systems to counteract that, which I'll just briefly talk about. So hydroxyl radicals, what happens is I'm going to pair up that electron, I'm going to break the HBr bond, and I'm going to pair up the H dot that results from that with the OH dot. And then I'm going to break, when I break the HBr bond, I'm going to give that pair of electron, or that unpaired electron to the Br. So what I'm doing is, if you're not quite following where all the arrows are going, here's what I'm doing, except this isn't formally what I'm doing. I'm taking the HBr bond and I am treating it as if it is two unpaired electrons. I am taking the hydrogen unpaired electron and pairing it up with the OH unpaired electron, and then the bromine unpaired electron it's taking back. Now, what would the transition state look like? Transition states for free radical reactions have no charges, because I have not written a charge at all, nor will I. So what happens is that what bond am I forming? I'm forming the OH bond. What bond am I breaking? I'm breaking the HBr bond. So there's my transition state. There's no charges to work with. So it's just about what bonds am I making, what bonds am I breaking. I'm breaking the HBr bond and I'm making the OH bond. Okay. And so that leads me to form water, and that leads me to form a bromine atom. I'll call this a bromine radical, but really, to be honest, this is a bromine. If I put in the rest of the lone pairs, it's a bromine atom. But it is still has an unpaired electron. So this is the initiation step. The hydrogen peroxide, when you heat it, or just naturally, it will break apart like this to form two hydroxyl radicals. The hydroxyl radical then reacts with HBr. And notice, because of the fact that with an unpaired electron, species have an odd number of electrons, on the left-hand side, you're going to have a total odd number of electrons, and on the right-hand side, you're going to have an odd number of electrons. So one of the insidious things about radicals is when they react, they always generate another one. So they continue along. It doesn't take more than a few of these radicals to cause the reaction to occur, because every time they react, they generate another one. So that's a problem with free radical reactions, is how do you stop them? And we'll only talk a little bit about that here, but we'll talk more about it when we do full-blown free radical halogenation. All right, so then what does the Br do? The Br dot is going to add to the double bond. So I'm going to reverse my double bond here and write CH2 and then my CH with my CH2, CH3. Now, let me again, just for the sake of showing you what's happening, I'm going to write the double bond as if it was two unpaired electrons. So here's what can happen. What can happen is I could take those two unpaired electrons and say, you know what, CH2, you get yours, and CH, you get yours. Now, this is not what happens, but I'm illustrating the choice that the bromine has. The bromine can either pair up its unpaired electron with the CH2 unpaired electron, and it will form the bond to the CH2, leaving the CH with its unpaired electron. In other words, the bromine adds to carbon 1 in this case. Or the Br dot can pair up with the CH dot, leaving the CH2 with its unpaired electron. So if this is carbon A and this is carbon B, addition to A will produce that radical, addition to B will produce that radical. Well, which one of these is going to be the major intermediate? Which one of these two radical intermediates is more stable? A or B? Okay, what is A? What kind of radical is A? Primary, secondary, or tertiary? A is secondary. It's a secondary radical. What is B? B is primary. Which radical is more stable? Secondary is more stable. So that means I'm going to form the secondary radical more often than the primary radical. Anybody getting a sense of deja vu here? When we added HBr, what did we do? Almost exactly the same thing, right? We added the H plus to carbon A, we added the H plus to carbon B, and then we got two carbocations, and what did we say? The H plus will add to the carbon that gives us the most stable carbocation. But what have I done in this case? Because I'm doing this with radicals, I've changed what's adding. So instead of H that's adding, it's now Br. And instead of the more stable carbocation, it's now the more stable radical. But same principle holds. So in other words, I'm going to form the more stable secondary radical in this case than primary. Then what happens next? What happens next is, in the final step, I'm going to take that major product that I just made, and it's now going to react with an HBr. So I'm going to split the HBr bond again. The pair of electrons from the hydrogen, or the unpaired electron that the hydrogen gets, is going to pair up with the carbon radical, and the bromine ends up with the other unpaired electron. What's the transition state going to look like? The transition state is going to have the CH partially bonded to the H, and then that H is partially bonded to the bromine as the HBr is breaking apart. So in the transition state, I've got a CH bond forming and an HBr bond breaking to give me then the final major product of the reaction, which resulted in, I guess, the Br adding to the carbon with the most hydrogens and the H adding to the carbon with the least hydrogens, anti-Markovnikov.
Does this not, like, you said that it'll be 100%?
No, this will be the major product, but it will not be the exclusive product. So in other words, we will get as a minor product, we will get the other reaction where the HBr bond will break and pair up with the CH2 dot. That transition state will again have a partial bond to the bromine, a partial bond to the hydrogen. Sorry, the other way around. Partial bond to the hydrogen, partial bond to the bromine, and then that will be that transition state. And then the minor product in this reaction is going to be what would be the Markovnikov product. So will we get both? Yes, we will get both. This will be the minor product, though. It'll be a lower percentage. This will be the major product, which will have a higher percentage. But it won't be exclusive. We will get both products because it's only secondary versus primary. And primary radicals are stable. They're not as stable as secondary and tertiary, but they can form, I guess, is what I should say. So notice that in the final step of this mechanism, what happens is that I react the carbon radical with an HBr, and I made, which I did not write, I made another Br dot. That Br dot then adds into another double bond. So basically, if you just had a single hydrogen peroxide break apart, that would be enough to cause the entire reaction to occur, because when it reacts, it forms a Br dot. When the Br dot reacts, it forms another Br dot. So the process just continues. And when does it stop? It stops when it runs out of alkene. Or the other time it stops is when two radicals come together to form a covalent bond. And we'll talk more about that step when we talk about free radical halogenation after break. So this is a multi-step mechanism. Now, what I should do is I should go back and write, because I broke the bond up here into the two unpaired electrons to just show you what was happening. Let me rewrite that second step exactly how we would write it. So in terms of the second step, it would look like this. You would have your Br dot, your CH2 double bonded to your CH. And so the way we would write that is, if I'm going to add the Br dot to carbon 1, I'm going to have this, I'm going to break the double bond apart. The carbon on the right is going to get an unpaired electron. the unpaired electron that the carbon on the left would get is going to be paired up with the bromine's unpaired electron. So you'll notice with the fish hooks, whenever we're forming a bond, I like to draw the fish hooks so they're kind of coming together, showing that that bond is being formed. The transition state for that would be the bromine partially bonded to the CH2, the double bond partially breaking, and again, the transition state for these kinds of reactions are just partial bonds, no charges. And there is no such thing as, well, there is a delta dot, but we're not using it in this context. Okay. So then the final product, the final major product would be, of that step would be this. So that's how we would write the second step normally. Is everybody with me? Yes? No? Okay, there's one thing I forgot about that I forgot to include with the structure of the radical. So when you have a radical, it is sp2 hybridized. In this class, it'll be sp2 hybridized. Is it possible for it to be sp3 hybridized? Yes, but not in this class. So the radical then is sp2 hybridized, which means it has this structure, which when this p orbital was empty, that was a carbocation, but now it's a radical, so that p orbital contains the unpaired electron. And that unpaired electron is going to spend 50% of its time in both lobes. Okay. Which leads us now to the third part of HBr peroxide. HBr and peroxide adds HBr, anti-Markovnikov. What about the stereochemistry? So in other words, if I was to take this double bond, and I'm going to put two methyl groups here. So it doesn't matter whether I add the Br dot to the top carbon or the bottom carbon, I'm going to get the same product. When I do that, let's say I add the Br to the top carbon. Down here, I'm going to have my sp2 hybridized radical. When it goes to react with HBr, is the top lobe or the bottom lobe going to be the one that gets the H? So is the H going to add to the top lobe, bottom lobe, or 50-50? Give me an answer. Top? Give me another answer. Not that you're necessarily wrong, but let's get more answers. I mean, we could just go around to everybody. We could vote. Let's vote. So A is going to add to the top, B, it's going to add them. It's going to add bottom, and C, it's going to add 50-50. Okay, we ready? All right, I have 11 to 5 to 7. So I think we need a minute to discuss and revote. Discuss and then we'll revote. Are we ready to revote? Okay, A top, B bottom, C 50-50. Now we're at 16 to 8 and 1. And 16 favoring 50-50. So the critical part of this is a radical is an sp2 hybridized intermediate. And just like when we have a sp2 hybridized intermediate of a carbocation, you add 50-50, you will also add 50-50 with the radical. So one of the things we're going to say is that you always get 50-50 whenever you have an sp2 hybridized intermediate. Our two choices are carbocations and radicals. So in this case, it is going to be 50-50. I'm going to add the H 50% to the top, and I'm also going to add the H 50% to the bottom. So that I'm going to end up with 50% cis addition and 50% trans addition. So in this case, it's going to be just like carbocation, any Markovnikov addition that went through a carbocation. Okay. Now in reality, you can sometimes do chiral additions with a free radical, but that's going to be beyond the reactions we're going to talk about this year. So whenever we have a radical reaction, it's always going to basically produce a racemic mixture at that carbon, just like SN1. Right? So HBr with peroxide adding HBr, anti-Markovnikov, 50-50. Because the other thing we need to do is we need to generate a table of all the reactions that we've learned. And usually when I generate the table, I have 3 columns. What am I adding? How am I adding it? How am I adding it? And then I have actually a 4th column that says notes. Notes include things like triangle, trans, square, cis. 5-membered ring, cis. Carbocation, 50-50. Radical, 50-50. Okay. So those are our basic sort of fundamentals that we need to know in order to be able to write the products of the reactions completely. We also need to know that because now we have to define these reactions as being stereo or regioselective. And there are some rules that we can use for that. Okay. All right, so is everybody okay with the free radical halogenation? As far as the mechanism goes, I could ask you to write the mechanism, which would be initiation step, this second step, and then the third step of the alkyl radical reacting with HBr. And you will see examples of that in some of the older exams. Okay. So now let's talk about regioselectivity. So regioselectivity has two parts to it. Regio and selectivity. I make that a point because let's define what each one of those means. First of all, what does it mean to be selective? It means that you are doing what? You're choosing one over another, right? You're choosing one of a number of possibilities. If you do not have those possibilities to choose from, you cannot be selective. Okay. So, there are times when you have no other choices, you cannot be selective. You'd like to be, but you can't. Same thing's true for reactions. Only in the context of reactions, what does that mean? That means we have a major product and we have a minor product. If we only form one product, we are not selective. The reaction is not selective. Okay? And here is the other thing about these terms that doesn't quite make sense, but this is the way they've defined it. The minor product may be 0%. The major product can be 100 to 0, or it can be 50.1 over 49.9. The major product is the majority product, but it may also be the exclusive product in terms of selectivity. Okay? And that's gonna be a little tricky because one would think that if a reaction went 100 to 0, there would be another term for that. There isn't. Okay? And then this is going to come into play with the stereo selectivity. But selective means we have more than one product, and one of those is the major product. Regio means that of the products I'm choosing from, they are structural isomers. And structural isomers means that the atoms are bonded differently. And so regioselectivity means that I am making more than one possible structural isomer, and one of those is the major product of the reaction. And then there has to be sort of a systematic way of predicting what that product would be. So that's what regioselectivity means. Okay, here is a reaction. Is this regioselective? Well, what am I adding? HBr, an H and a Br. How am I adding that H and Br? Well, there's two possible ways for me to add it. I can add H to the CH2 or H to the C with the CH3. So there are my two possible products. Are they structural isomers? Yes, the atoms are bonded differently. How do you know two things are structural isomers? They have different IUPAC names. Do those two have different IUPAC names? Yes. 1-bromo, 2-methyl cyclohexane, 1-bromo, 1-methyl cyclohexane. They have different IUPAC names. Did I select one of those as a major product? Which one is the major product? The one on the left or the one on the right? Let's vote. Which one is the major product? A, B, or they're 50-50 C? Which one's the major product? A, B, or they're 50-50? Twelve, 7, 4. Kind of hoping better for that, but discuss. Okay, are we ready to vote, revote? Some of us are, since we're discussing hair care products as opposed to the reaction at hand. Okay, A, B, or C, the major product of this reaction after your discussion? All right, now we're down to 17 to 8. All right, I'm adding HBr. What am I adding? H and Br. How? Markovnikov, anti-Markovnikov. Markovnikov. That means the hydrogen goes to the carbon in the double bond with the what? The what? The most amount of hydrogens. Markovnikov means the hydrogen is going to add to the carbon in the double bond with the most hydrogens. That's going to produce product. You're the H plus. Are you going to add to carbon A or are you going to add to carbon B? Oh, tomorrow's going to be really bad. So those of you that show up, Be more active, or else it's going to be really, really, really bad. The energy is just going to be sucked out of the room. H plus is going to add to carbon on 3. 1, 2. Thank you. Which makes product B. But wait, your vote was 17 to 8A. Guess we can't trust your vote. So B is the major product. That's the Markovnikov addition. So this reaction is regioselective because it's selecting product B over product A, which is possible to be formed. And so it has two products. It's chosen a major product. And the systematic reason for that is Markovnikov addition. Okay. So this is an example where you have regioselectivity. Okay. So number one, regioselectivity means the reaction is Markovnikov or anti-Markovnikov. Okay, it's easier sometimes to figure out when the reaction will not be regioselective. So number one reason that the reaction is not regioselective is because it is not Markovnikov or anti-Markovnikov. A reaction will not be regioselective then. Now, what kinds of reactions have we done? This is a dangerous question because I'm going to be disappointed in the lack of answers. But which reactions have not been Markovnikov or anti-Markovnikov? Give me an example. Cis-hydroxylation. Close. That's okay. Cis-hydroxylation was not. What did you say, Olivia? What else was not Markovnikov, anti-Markovnikov? The mercury was. The mercury was Markovnikov. But there's a time when it won't be, and we'll come back to that. But which reagents were not Markovnikov, anti-Markovnikov? Br2. What else? The KMNO4 with base, which was a cis-hydroxylation, was not. The other KMNO4 cleaved, it's not a choice. Yes, it wasn't Markovnikov and anti-Markovnikov, but cleavage isn't going to be regioselective. What else? Yeah, but you're adding that, right? Yeah, so that was Markovnikov usually. Again, there was a time it wasn't. I'm looking for one more. Epoxides aren't really the addition to both things, so I'm going to leave those off. How about hydrogenation? Hydrogenation, when we added H2, was not Markovnikov or anti-Markovnikov. What is the characteristic of all three of those reactions? And the reason why they're not anti or Markovnikov. In those reactions, what am I adding to the double bond? Two of the same group. Two OHs, two BRs, two H's. Whenever you add the same group to the double bond, it can't be Markovnikov or anti-Markovnikov. And since in the end, I'm only making one possible product, and I'll illustrate that like this. If I add Br2 to this, what am I adding to the double bond? 2 Brs. Is there another possible product? Notice I'm not taking into account the stereochemistry because I will do that, but that's going to become stereoselective. Okay. If I add the same groups to a double bond, I only form one product. One structural isomeric product. Therefore, if you have a symmetrical symmetrical reagent, you are not regioselective. What about the alkene? If the alkene is symmetrical, will I get more than one product? Well, I'll let you think about that till tomorrow. Yes, we will be having class tomorrow. Yes, even if it's 2 people, I will be lecturing. Hopefully there won't be any crisis with my computer to record that. Man-made crisis or other, so it's always better to hear this live than on tape. So I will see you tomorrow.